Now that we know the meaning of the word modulo and we've already worked with a couple of problems, we can ask some pretty interesting questions. As a matter of fact, I've already mentioned the field of mathematics called number theory, and in that class or in that field, people are really interested in finding the modulo, especially when you divide by prime numbers. The reason why we care is because it has a lot of real good applications, for example, for encrypting and decrypting information. So it's a very useful operation. So for example, if I ask you right now to divide a number by 11 and you found out that the remainder is 6, well, what would 4 times the original number divided by 11 give you as a remainder? So for example, if I said 17 mod 11 is equal to 6. When you divide 17 by 11, you get an answer of 6. Then what would 4 times 17 give us if we divided that number by 11? Now keep in mind that this is 68. So the question is, how much is 68 mod 11? And it's simple. In this case, the answer is going to be 2, because 68 divided by 11 is going to be 6 with a remainder of 2. So 2 is the answer, but is that true when I change the number 17 to something else, for example? Is it always going to be 2 at the end? Now what I just did over here is not a proof. This is just a quick reasoning that I do on a scratch paper to kind of get an idea what the answer is supposed to be like. But this would not be a proof. This is only going to work for 17, but does it work for something else? Well, pause the video for a minute and see how you can go about proving that the answer is always going to be 2 no matter what number we begin with, as long as the number divided by 11 is equal to 6. The solution goes something like this. We know that m modulo 11 is equal to 6, so that means that when m is divided by 11, the remainder is 6. Now, this modulo business is a brand new operation. We have never worked with this before, and you probably haven't either. So a good idea is to rewrite that expression in terms that we can understand. We can rewrite it with additions and products using the quotient remainder theorem. So we can use the quotient remainder theorem to rewrite the original expression. And again, keep in mind that Q is irrelevant. It's a quotient, but we don't really care what it is. Now, we would like to know what 4 times the m has as a remainder when it's divided by 11. So let's multiply m by 4 and see what happens. Now, since m is 11q plus 6, when you multiply m by 4, that means you're multiplying 11q plus 6 by 4. Then I can distribute the 4 over. 4 times 11 is 44. 4 times 6 is 24. But I would like to write it in such a way where I have multiples of 11. That's because eventually I want to divide by 11. And if I have multiples of 11, I can ignore them because they divided by 11 will have a remainder of 0. So in other terms, what I want to do is break down the 24 into 22 plus 2. Why am I choosing that? I'm choosing that because 22 is an even multiple of 11. 44, Q is an even multiple of 11. So both of those, when they get divided by 11, can be ignored. The 2 at the end is not a multiple of 11. So when I divide it by 11, it's going to be 2 at the end. To make this simpler, I'm going to rewrite the expression as 11 times 4q plus 2. So you can see this is now an integer, and this is 11. So in other terms, what this is saying is that if I divide 4m by 11, then the answer is going to be 2, which is written at the very end. So this means that 2 is the solution. It is the remainder when 4m is divided by 11. So our original guess when we did the 17 divided by whatever 11, which was modulo 6, then we multiplied it by 4 and we kind of estimated the number to be 2. Our estimate was actually in fact correct.